Hey guys, I'm Karthik from Facebook, and I'm going to talk to you guys about the infrastructure behind Facebook messages. I know Anand said we shouldn't think of ourselves only as big data, but this one's all big data. So what is the new messages product that we came up with? So to give you guys, to put it in perspective, right? The new messages was about, you may know somebody, Bob, who only reads email, or you may know somebody else, John, that only checks his SMS, especially if they're like some of the cousins I have. But anyways, the deal is, you don't have to think about how you want to reach a person. All you want to think about is the fact that you want to tell them something. And that was the vision behind this product at Facebook. So in order to achieve that, what we did was to combine the different channels of messaging under one umbrella. So you have the traditional Facebook legacy messages, the chat messages, emails, and SMS. So bringing all that inside, you don't really have to care about how a person receives it. The person getting the message can actually opt his option and receive it in that fashion. So with that background, I'm going to give you guys some quick facts. We used Hbase, Hdfs, and MapReduce quite heavily to put this into production, so that's pretty much going to be the focus of the central theme behind the talk. So what did we estimate back then? So we had about 15 billion messages coming in every month, and this was without SMS and legacy email. And email is just the traditional chat messages. Traditional Facebook messages. And if you assume about a 1 kilobyte size per message, that comes to about 14 terabytes, and 120 billion chat messages, and that's like always growing. So a total of 25 terabytes. And this is normalized data. That means if 3 people are involved in the conversation, the message is stored just once. This was stored on MySQL, so the normalization, we actually cared about keeping data not too big so we could actually handle it. What do we see now? Well, we obviously didn't, these sizes don't factor in the metadata that we have to put in and such. So what we're seeing right now is about 300 terabytes per month, and that size is compressed and unreplicated. Another factor that actually has blown up the total data size is the way users interact with the product itself, which is another thing that's really hard to predict. So what do we store? We have 2 main storage technologies. We use Hbase and Haystack. Haystack powers our photos, and Hbase is something that all of you guys are decently familiar with. So in Hbase, we store the metadata for the messages, the search indices, and the message bodies if they don't cross a certain size threshold. In Haystack, we store attachments, if any, that come with emails or messages, and the very large message bodies. The reason we did this was because Haystack is really good at powering Facebook photos. It's been working pretty well. We have a really good ops team built around it, and it really handles cross-data center replication, which becomes a major concern if your data sizes increase quite a bit. All right, why did we choose Hbase? Right from the get-go, we had thought about fronting Hbase with an application server. So we thought that the storage underneath would see a write-dominated workload. So a high write throughput was one of the important characteristics we were looking for in whatever we chose. Another thing was the fact that we don't know how this is going to grow, and we have hundreds of millions of users at Facebook sending messages, so it needed to scale pretty quickly by just throwing in some machines. When you have a lot of machines, failure is the norm. So when one machine goes down, another must take its place. We can't really say, like, how it's going to fix this machine up while it's down and then serve the data. So automatic failover was a super important thing for us. And lastly, we get the benefits of Hdfs. What benefits of Hdfs, you may ask? So the slide. Hdfs is fault tolerant. All of you guys know about Hdfs, so I'm going to go pretty quick on this slide. So it's pretty scalable. You can throw in a few machines and scale it out. If data becomes corrupt on disk, it has checksums so that it automatically replicates the data and keeps the replicas in sync. And it comes with MapReduce built on top of it, which is really useful for a variety of different applications. And last but not least, Hdfs is pretty heavily tested in Facebook. We have a petabyte scale warehouse cluster and a ton of dev and ops experience, so we're pretty comfortable using Hdfs as a storage. Okay, so moving forward, how did we architect our messages, right? So The whole thing is going to center around Hdfs, Hbase, and Zookeeper, which is the central thing that's used by the Hbase subsystem. So Hbase is a distributed database layer that uses Hdfs underneath for storage and uses Zookeeper as a coordination service to handle failover and availability and all those kind of concerns. So this is what we used to store data. All right, so how does this fit into the big picture? So that box right there represents that entire subsystem. And like I said, we always wanted to put an application server in the front to take out most of the reads. Each user would be sticky to a single application server in that application server cluster. And this is what we decided to call a cell. A cell for us was an independent failure domain. Now, each user would be sticky to one application server, which would talk to the Hbase, Hdfs, and Zookeeper subsystem underneath and get the data for that person. Now, we scale out by just adding more and more cells. So this is useful for a variety of reasons. We'll go into what a cell means and how it helps us in a bit. But now that we have a bunch of cells, a user is always sticky to one cell and to one application server in that cell. So that means we need a service which tells us, given a user, which cell does this user live in. So that's the user directory service. And I was referring to Haystack in a previous slide, so we'll throw that up there too for completeness. All right, so we have all these machines and this sort of a stack architecture, whatever. So let's walk through how it really all works. So we have a client, the web server or what have you, actually trying to perform an operation on any user. So let's say a user gets a message. How does that work? So the user gets a message. The first thing the client does is goes to the user directory service and tries to look up which cell does this user belong to. Having gotten the cell, the client goes and talks to the exact application server, if it can find it. Otherwise, it talks to any random application server, which forwards it to the correct application server in order to add the message. If the application server deals with all the business logic. So if the message had an attachment or a very large amount of data, it actually strips that out, puts it in Haystack, stubs out a handle, puts it back in the message, and writes that into Hbase. So Hbase then stores the actual metadata, the message, if it's not too big, and the search index. So why did we go with multiple cells? Well, the biggest advantage multiple cells give us is the fact that if we ever had to upgrade and say the change was not backward compatible, we would actually need downtime to upgrade the entire cluster. And having multiple cells would only cause this to be a downtime for a fraction of the users and not the entire user base. And the second thing was bugs that would take down the entire cluster. And if that ever did happen, then we wouldn't have an outage across the entire user base. It would just be for a fraction of the users. Now, having different cells means we could put different versions of Hdfs on them, and we would be able to detect bugs or regressions or whatever much quicker than having to put it on one behemoth cluster. But of course, we'd have to track the versions on different cells, and until recently, the Hdfs protocol would not work. It was not backward compatible. Like if we bumped the protocol version number, you couldn't talk to other cells. So these cells had to be independent domains. OK, what is a typical layout of a cell? So we have 5 or more racks, and that number is dictated by the fact that you need at least 5 machines for Zookeeper, so to reach a quorum and still be available for long periods of time. So let's throw 5 boxes in there, 5 racks. Now, the top of the rack node on each of these racks, the top machine is something that we call a controller node, and is really sacred for us. If it goes down, people get up and fix it as soon as they can. Because all of them run Zookeeper. 2 of them run the name node and the secondary name node. 2 of them run Hbase master and the backup master, and the job tracker on the last. So that's the 5 machines. We have 20 servers per rack. All the other, except the top of the rack machine, every other machine is a slave. It has the Hbase slave process, which is the region server, the DFS slave process, the data node, and the task tracker, which is the MapReduce slave process. So that's how it looks. And to give you guys some more details, each of the machines is a 16-core machine, 12 disks, 1 terabyte, and 48 gigs of RAM. So, and operationally, we noticed that we have a lot of top-of-the-rack traffic. That's just because we set our replication factor to 3, and we want to have cross-rack replicas. And and the workload is I/O bound. Okay, so with that quick overview, I'm going to go and give you guys a flavor for what are some of the surrounding auxiliary systems we had to build. One of the biggest ticket items that we had to do was to build a separate backup system. And so back then, when we were putting this thing into production, this was the first time we were going to subject it to a super real-time workload at such a large scale. So naturally, we wanted to have another source of keeping backups. We didn't want to put the backups in the same system that we did and put into production, so that in case there were bugs, we could actually recover from it. So we used Scribe for backing up. And we did logging from both the application server machines as well as the region servers. It's because Scribe is lossy, so in order to cut the losses, we logged from 2 places. So that's twice the amount of backup. So naturally, then we had to merge the data that we logged and dedupe it and store it, and that would be the final backup. Now, with every backup system, it's no use if you can't actually use it when it's needed. So we had to build something that would restore the data. And of course, what's the point if you could still restore it, but you didn't know what to do when the time came up? So we had to keep testing it and making sure it really worked, and we knew the fire drill and all that good stuff. Okay, so you'd ask, you already have 3-way replicas. Why do you need backups, right? So, and I could give you like a bunch of justification, but nothing works as well as a real example. So there was actually an operator error. One power cable, I believe, was unplugged, and I don't know how, but 60% of the machines went down in the entire cluster. So, well, the power was brought back up in a few minutes, but we were lucky that there was no data loss. Otherwise, in certain scenarios, like when you're major compacting, deleting data, purging it from trash, what have you, we could actually have lost data. But if we did have our backup. So, we're convinced that we put in good work there. And that's an extreme case when we actually survived. So, okay, moving forward. So, backups. Lots of code in Hdfs and Hbase in the forms of enhancements. So a whole Hdfs append branch, the whole community was involved in this. So, and we had to get this to support a real-time workload, get Hdfs to support a real-time workload so that Hbase could work well with it. And we rewrote a good portion of the Hbase master so that we could have a true master failover. And the new master came up, it would know where the old guy left off, and there's no data just in the memory of the old master that's critical to operation. One of the other things was the block placement policy of scattering data across, like putting replicas on any machine, has the advantage that if you do lose data, you lose a little bit of it. But in our case, losing any data was pretty much game over. So we came up with a new block placement policy so that if you did lose data, you would lose a lot of it, but the probability that you lost data was really, really, really low. And we had to build a ton of monitoring. So this is like a huge ecosystem that we had to build around our production machines, in the sense that we had to remove machines that were bad disks, could not SSH into machines, and all that stuff automatically. And we find that 5 to 10% of our clusters always have machines which have some problems or the other. So that's commodity hardware. Oh well. Okay, so another thing that we had invested in quite a bit was the fact that we wanted to upgrade Hbase in a rolling fashion, which means we wanted to upgrade the software but not really have any downtime if we could avoid it. Naturally, this will only work if the upgrades are actually backward compatible. So the way we did that was we upgrade and restart the primary master. So the primary master would go down for a split second while it restarts. So the secondary would take over and the primary would get upgraded. But the secondary is actually in control at this point. So then we upgrade the software on the secondary master. So the primary goes down, restarts, and the primary takes over, the secondary is upgraded. So at this point, both masters are upgraded. And then we restart a certain percentage of all the region servers in a rolling fashion so that Hbase automatically fails over these regions and assigns them to other region servers. They start serving data, and you get a whole upgrade without actually without any downtime, or very minimal. Okay, so moving on to another of the challenges that we faced. So I've talked to you guys about what we built, what we have, what the architecture is. So to give you guys a flavor, we used Hbase and MapReduce outside the production context to just move data. So putting a new messaging system like this into production is hard enough, but having to move data from one existing messaging system store into another messaging store is actually at least as hard, So first, the layout of the legacy messages, right? So each of these blue boxes represent a database. So the two interesting things in this diagram are that the users are scattered across all the databases by the user ID. So a given user could be on any random database, and you'd have to look up and know which database to go to fetch that user's data. And the second thing was, since it's normalized, this is MySQL, it's normalized data store, so the message IDs are also scattered by the message ID on different databases. That's because the message is just stored once. There could be 10 people sharing a message, the message is stored once. And in MySQL, we wanted to restrict the total size of data we stored. So what does that mean to look up any one user's data, right? So we have a user 1. So in order to look up the message ID, we go to the database that the user has and fetch the list of message IDs. Now, with this list of message IDs, we have to go to each database that has the message and go fetch the message data. So what does this mean for migration? Just do that, but do that for all the users, do that fast, and don't take down the production site. That's kind of what it is. So the challenge really comes in because once you start hitting a larger and larger set of databases, because for a larger set of users, you hit all the databases, some of them could be down temporarily, and what do? Like, you have message IDs, you don't have messages. So you have these kind of inconsistencies, and this is a simplified diagram. There's a few more tables to join in there. So the way we did this was, in order to fetch data for any user, we would always process in bulk, right? So when we're migrating, like, we don't care how long it takes for a single user, as long as we can do a lot of users in a given period of time. So we wrote a lot of MapReduce processes to bulk process users. We do millions of users at a time. And the idea was, from these millions of users, we'd pick users and partition them according to the databases on which their data lived in the partitioner. And in the reducer, we'd go make one connection to those databases and process as many users as we could. Now, some of the tables we can scrape beforehand, keep it ready, and then do an incremental scrape and keep doing that, but sometimes you cannot. So because you may not have a timestamp on which you can do an incremental scrape, like, and primary examples are deletes or mark as unread or something like that, where you don't really know when the person did this update, you just see the final value. So in that case, we fetch the data right before. And in order to store the data, whether we fetched it right before the migration or whether we always had a stored like a dumped copy that we had and incrementally scraped and updated, we used Hbase for migrations quite heavily. And when it was possible, we stored the entire data, and we would periodically catch up to the production databases, and while doing the migrations, go to production to just fetch the deltas. And for the other cases, we would fetch the entire tables on the fly and dump them into Hbase and create an Hbase table. What are we working towards here? So once we have all the tables, we do a giant join. So we use MapReduce for that quite a bit, and we would try to optimize, which tables we start. And so it's a giant Hbase join across 2 or 3 Hbase tables. And one of the things we had to do was to detect the fact that you may not always get data. So in a previous slide, I was telling you, like, some of the databases could be down, so you could have partial or incomplete data. Well, to us, it may be like a 0.01% occurrence, but to the user, it's like, where are my messages? So, we had to detect that case, fix it, and so on. Yet another challenge is what we built here at Facebook is an inbox, a social inbox. So it's messages that matter. So it's messages from friends and friends of friends. Now, that's awesome when you look at the inbox, but when you're actually moving the messages across, that means for every single message, you got to figure out that the person that sent it, is he a friend? Is he a friend of friend? Or is it a message that's worth keeping? And in more engineering terms, it means let's join a bunch of more tables in and do it fast, and don't make it too stale, and of course, don't take down production databases. So yeah, that was another thing we had to balance, but here's another interesting problem. Let's say we're starting to migrate millions of users. It's going to take a few hours for the users to get migrated. Guess what? They don't stop sending messages. So we have to get these messages that the users send and receive while they're migrating, and we have to put them into the final store. So in order to do this, we started double writing. Our user is marked as in migration, and the minute they're marked as in migration, we start writing to the final Hbase destination that their data is going to be served from. But the application server would then see a message come in that's like the 5th message in a chain of 5 messages, but the first 4 are not yet there, so it doesn't know what to do with it. So the application server has a state that we flip, where you just start silently writing it to Hbase without interpreting the data, and once we finish the migration for the user, we flip a switch and say, okay, now go and interpret the data. But of course, this process And well, the double write could also fail, so we have to throw it in a queue. So all that, long story short, we could see duplicates, which means we have to dedupe that. So here are some interesting snippets from our experience using Hbase, MapReduce, Hdfs across the board, like trying to migrate the user's data. So it's all about throughput. It's not a latency game. It's not about how fast you can migrate a single user. It's about how fast you can get the whole batch done. So we worked that way. So two of the most common and recurring themes in our MapReduce jobs was that, like, we wanted to maximize the number of Hbase ops that we did using MapReduce. So in order to do this, we used a partitioner, and well, simply we would split, the partitioner would take the key space and split it according to the Hbase regions. But that was not enough to maximize ops, so we had to actually increase the key space to have like n different partitions per region. And the second thing, which is probably true of a lot of MapReduce jobs in general, is that we wanted to avoid the long tail, which is that if you have 100 MapReduce jobs, 99 of them finish in a minute, but then the last one took a day, so the job took a day. So we wanted to cut that and make sure that all jobs were finishing roughly at the same time, so we architected all our MapReduce jobs that way. And the last thing was, whatever data we migrate here is backup data. It is useful data. So we had to output the data in such a way that our backup and recovery systems would also understand. So, you know, that's another of the things. All right, so I'm going to give you guys a very quick flavor of what we are thinking about internally with respect to Hbase and Hdfs and what the road ahead looks like. So Hdfs. One of the things we really want to work on is the name node HA. It's been mentioned a couple times before. The idea is that today, if the name node goes down, the secondary name node has to be promoted. The entire Hbase cluster would go down. So we want to be able to avoid this. We want the secondary name node to be able to take over like pretty seamlessly. And this is something where we have some code for, we have a direction for it. It may not be the final solution, but it's an intermediate step that'll get us there. And it's already deployed on a warehouse cluster, and it's being baked there. It's not yet in production for us. Yet another thing is perf. It's never enough perf, right, until you can prove it. So we want to improve the read path, the write path in Hdfs so that we can serve this real-time workload, serve more queries with the same set of machines. And a third thing we're looking into is how we can use Flash to improve performance. All right, on the Hbase side, the things that we care about there are fast, hot backups. So we have this separate backup system, which is great and all, but it's not really scalable, and it's not something we want to be doing forever. So we want to replace this with a backup system that works and we know is reliable and quick. Yet another thing is cross-data center replication. How do we handle that? Even if it's being handled at the application layer, there are certain things that Hbase or the DFS underneath may have to expose so that the application layer is able to do the data center replication. Secondary indices, something that always pops up like once every so often about Hbase. Online schema changes. So some of the schema changes today in Hbase, because it has to be made on so many region servers, it's a distributed database, we have to take down the cluster or at least disable the table and stop serving data. So we want to be able to do that in a more online fashion. And last but not least, improve perf, right? Like as engineers, we can never get enough perf. So with that, I can open it up for questions. Thanks.
Hi. I have a number of questions, so I'll try to share the mic, though.
All right.
How many jobs do you run against the message data? Do you use the Hbase mostly for online storage or mostly for jobs?
I'm sorry, like I got the first part. How many jobs do you run against message data after that?
So do you use Hbase mostly for online storage of the messages or mostly for running jobs against
No, we totally serve online message data for Hbase, so we're using it in production capacity to serve messages. We also used it offline to store messages and enable us to run jobs against it and migrate. So we do both.
Cool. And the latency goals when the messages are served out of Hbase, what are your goals there when they're not cached?
So that question is harder to answer with a simple number because sheerly because the messages are of different types. There's like something from chat all the way to email. Something could have attachments or none, and the way it's being rendered. So it's something we keep a handle on in terms of 75th percentile, 100th percentile, but there are no hard numbers, and it's something we're trying to learn as we grow the clusters ourselves also. But our primary goal was zero data loss and the ability to handle a lot of data.
Got it. And the search index, is
Yep.
that an inverted index stored in Hbase? Or
Yes.
do you use Lucene? Or
It
all
is
in
it is a
HBase?
full inverted index stored in Hbase and for each user and each user's entire mailbox.
Okay, and last question.
Go for it, man. Go for it.
Are users dynamically moved across cells or servers, or how do you manage
So
that?
users are definitely dynamically moved across servers because if a server goes down, like an application server or whatever, the user has to be served no matter what. So that was definitely something that's of paramount importance to us. As far as moving between cells, the idea was it is important for us to do, but not necessarily in a super dynamic fashion. It could be that we would compute a certain set of users, but we're not doing that right now. But the design is flexible enough to allow that.
Thank you. Great talk.
Absolutely.
I have one question.
All right. Any other questions?
Can I?
Sure.
Can I
Yeah,
ask?
yeah, sure. Go for it.
So actually, I have two questions. My first question is, I think you've done a lot of awesome work on improving Hbase and Hadoop. Are you contributing everything back to Apache, or is
Yes,
it going to be your
yes, we have contributed a lot of the stuff back to Apache, and the little bit that we haven't is only because we just had no time to do it. So there's full intention to do it.
Cool. My second question was, in Hbase, every region is served by only one server.
In Hbase, each region is served by one server. In fact, a bunch of regions are served by one region server, so it is automatically sticky that way. So a key belongs to a region, and a bunch of regions are owned by a server at a given point of time.
My question was, when a region becomes hot,
Yes.
Does it happen in online serving that?
Yes, it does, but one of the things we did was we hashed the entire key space with like an MD5 or one of those kind of hashes, so we automatically distributed it, so the probability that any one region got super hot is really low.
Okay.
The thing that we give up on was sequential scans, but we don't really care about sequentially scanning users, so.
Okay. Thanks.
Sure. Somebody here had a question, yeah.
So you mentioned about avoiding long tail, right? So
Avoiding, I'm sorry?
the techniques which you use to avoid long tail in your
Yes.
MapReduce jobs.
Yes.
So apart from speculative execution, like what other things?
No, it's not just that part of it. The jobs itself could be designed in a different way. Like if you're doing, you could transform a join that could be more efficiently done into a slightly less efficient join. Like let's say you're joining ID1 of one table and ID2 of another table. Like you would maybe have read ID1s and then have joined it with ID2s. What we do is explode the key space and try to get each mapper to work on a fixed set of keys that don't take too long, as opposed to taking one ID1 and having to read a whole lot of columns from the other table. Like, I mean techniques like that. But the aim was, the aim is not, let me do the minimum number of disk IOs. The aim is not, let me be the most efficient about writing the join, but the aim was, let it take the least amount of time to finish.
Thank you.
All right.
Oh, my question is actually the same as his.
Sure.
So actually the long tail one.
Yes.
So he already asked.
Oh, same thing. Oh, awesome. Beautiful. That's two birds in one stone. So.
I have a question. Do you conduct analysis out of the same cluster that you serve production data from, or do you move the data to another cluster for analysis?
So we move data to another cluster. Right now, we don't do that much analysis yet, but if we were to do it, we would definitely do it on a different cluster. At least that's the way it stands today.
Is the logic behind that? Is that just a performance issue, or is it sort of, what's the reasoning behind that?
So one of the things we have had trouble with is that it depends on who writes the job to analyze the data. So if a bunch of users start writing jobs, it gets very hard to control the amount of CPU it takes or the amount of memory it takes, and no matter how many settings you give, there's something always going to go wrong, and we didn't want to take that chance with the production cluster, but that's not to say, you know, if it all worked out, we wouldn't do it.
Hi.
Yeah, go ahead. Yeah.
Just a quick question.
Sure,
Are
yeah.
you going to do open source for Haystack?
That is something that I am not sure what our plans are. I think we would like to, but I don't know more than that. So.
Here? Did you consider using Cassandra here? And if so, it's over here. Did you consider using Cassandra?
Yes,
here?
we did. So
And why
we
Hbase?
actually considered using a bunch of different database technologies. One of the reasons we didn't go with Cassandra was that it is eventually consistent, and we, like I said, always wanted to front our store with an application server. So if the data heals from underneath, it's going to be very difficult for us to let the application server know that some data is stale or not. So that design didn't work out for one side. And on the second side, well, so for Cassandra, right, eventual consistency gives it the best performance. So hence, I'm assuming that we would use it in that mode. If we were to use it in strict consistent mode, it's not very different from Hbase or any other store. So that was one thing. And the second thing was that we have data coming in from a variety of sources like SMS and email and chat, and these have different inherent latencies, at least in the heads of users, if not in real life. So we really wanted to keep the data super consistent across these different channels.
How do you handle complete cell failure?
We try to bring it up as fast as possible, to be honest. So
Hi. Do you synchronize or mirroring your data across data center? So if one of your data center is down, would any of your customer get impacted?
So for us right now, I mean, that becomes a loose topic, kind of, but for us, for our first version, our primary goal was to get it to completely get supported in the data centers in which the data resided, as opposed to a data center failover. So that's something which we're investigating, exploring, and working through right now, but that's not necessarily been a concern as to how quickly can we serve the data. So if it meant a downtime, that's fine with us, at least for the first version, so as long as it is reasonable, of course. So.
Have you run into any issues with pauses during compaction for serving messages?
We do not run our servers super close to the edge, but so having qualified it with that, yes, GC pauses, Java, you know, everybody's nightmare. So, but no, that's not been an issue for us so far. Oh, Hbase compactions? Oh, sorry.
Oh, yeah,
okay,
Hbase.
sorry. Yeah, no, we don't see that. No pauses during Hbase compaction. We don't run our disks super hot, so we're fine.
Hi, could you share some of your thoughts about how you might handle schema changes in Hbase?
Yeah, sure. So our technique so far to handle schema changes has been, so one thing we can't do online, which is why the let us do this online stuff was there, was we can't create a column family on the fly, so we have to take a downtime on the table to create a column family. So some of the times we create spare column families and name them whatever, just so we're able to make it future compat. So depending on the type of schema change, if it's like, say, just a Bloom filter type change or something, then we just make the change, have to quickly bounce the table and the entire table, and then we're good to go. Or if it's like the actual disk format change, like, you know, the representation on disk change, then we populate the data onto a new column family using MapReduce jobs that run under some throttle. And once it's completely populated, we switch the application servers to using the new column family. Does that kind of answer the question?
I have a question.
Sure.
You mentioned that you're looking at Flash to improve performance.
Yes.
I was wondering, do you see a tie-in between 10 gigabit Ethernet on the servers and Flash, or there's a separate, you know, I've seen some data saying that 10 gig on servers may complement Flash in terms of better performance.
So we're trying to investigate how Flash would actually help us. So, and this is also very tricky because it depends on the way the application is written. Is it read intensive? Can it use a large enough cache, or is it write intensive? And do we have to buffer the writes? So it's very early days for us. So it's very hard to share any meaningful numbers on, you know, what we're going to use it for. But you know, it's just a bunch of ideas floating around or conversations going on. It's at the super preliminary stages.
How about just generally 10 gigabit Ethernet on servers? I mean, is that something interesting? I mean, do you think that may help improve performance for your clusters?
Yes, some of the clusters I think already have that, some of them don't. So we have to constantly balance between how much of network data we transmit versus how hard our disks are. So those are the two things we always keep touching. So if Flash helps improve disk quite a bit, then probably what you say is definitely the direction to go. So.
Hi. I have a question over here.
Sure. Yeah.
So I was just curious, do you observed any latency issues when you decommission nodes or running a balancer in the background so that the blocks are spread across multiple racks? They're moving across. So how is your locality gets affected there?
So the locality traditionally in Hbase is always affected every time even you do a restart because there's no locality for data. That's one of the things which we actually have just fixed, like it's super fresh. So that's definitely something that we're working on. But yes, upon a complete restart, yes, we do see a spike in the top of the rack, like on the total network transmission. But we try to keep our clusters as loaded as we can handle them. But we have test clusters that we shadow traffic onto, so we can push them and keep them quite ahead of the production traffic, like put more users on it and see. So that's the balance that we've chosen so far. So yes, we don't want to definitely get that surprise in production.